All right, so this is off Investigation 7, Expansion, Part 5B, Impulse and 2D Momentum. And this is number 6, so I'm going to try and work 6 and 7 and show you. This is a lot of times the way you see impulse is given in the graphical form. And so we already know that impulse, which is the symbol is that capital cursive I, equals a lot of things, but it equals, normally you see it as force times time, which equals the change in momentum. So really it's just Newton's second law with the time moved over. The units then would be Newton dot seconds, but normally those aren't the units, because if you're talking about an impulse, you're talking about two things hitting each other. They don't spin unless it's like two squishy lumps of clay or something. They don't spend that much time in contact. So assuming they hit and bounce off, maybe a tennis ball or a tennis racket would spin, on the order of 100 milliseconds together. But most things may just be together for maybe 5 milliseconds or for even microseconds as the amount of time. We watched a video demonstration of those two steel balls hitting and coming back. They were only in contact for 220 millionths of a second. And so the time there is normally really small, so normally Newton dot seconds is probably not the most appropriate unit. A lot of times it's Newton dot milliseconds or even Newton dot microseconds. And on really big, huge collisions, like where injuries, like in a car wreck, you might have something like a Newton microsecond. You might even have a kilonewton dot microsecond. Now I think that's what I would call a very that's a very large amount of force over a really small distance, and that's definitely considered an impulsive force. Okay, so anyway, I'll get rid of all that, but I'm just showing you those are some of the various units you would use for impulse. And what we have here, this is not that difficult of a problem because the graph's already given for you. As you'll see, problem 7 is much more difficult. But if we're given a graph and we're saying, okay, we have a force, and this force has a lead-in time, which most forces do. Most forces are not just either on, off, unless it's electromagnetics or electricity. Any kind of mechanical force normally has a lead-in time, and then it has a maximum period, and then a fade-out time. Okay, like if you're getting hit in the face, there is that initial contact, and then as it squishes in, that's your time. The force is increasing, then eventually it reaches a maximum, comes back. But you can think of this as koosh balls hitting, and if you have the lead-in times, see, I got a couple of them here. If I have, I'm looking at it, this koosh ball hitting this orange ball, the lead-in time would be this smash-in. See the way it's smashing together? So it'd be this smash-in time, and then right in here, and we're having to give an approximation because it really involves calculus, right? Because forces aren't going to have those diffraction points in them, but we have to give an approximation in there because it's an algebra-based course. In AP Physics, we do it from a calculus point of view. But anyway, you have that lead-in time, then it's maximum squish, and that maximum squish, to tell you the truth, probably a triangle. It's probably a better approximation because there's that peak squishness, and then it starts to reform. So this temporary deformation occurs right here, and that's where you're in this maximum amount of force of contact, and then the rest of it is this fade out. So this has got some kind of situation where there's a quick input, there's some kind of entanglement that occurs, and then it's a little bit of a slower fade out for this force of these two objects hitting. And we're supposed to figure out from there what's the impulse. Well, since impulse is force times time, you can start to get the feel that it's going to be the area. And so it's this area under the curve that we're trying to find. Well, like I say, because we're just doing algebra, we're kind of limited to 3 possibilities. I'll just write them down here. You can put them in your notes. There's 3 basic graphs we'll be looking at as far as impulse goes. And all of these are force times force on one axis and time on another. All right, so these graphs, this is the simplest possible scenario. You pick up a force at a certain time, and this is supposed to be a square. And then there is your impulse? Well, obviously the area is simply height times base. All right, so impulse in this case, in these general situations, is base times height. The other one, if you're going to complicate this some more, be a little more realistic, it's going to come down like that, and there's your impulse, is that area under that triangle. And as we know, the area of a triangle is 1/2 base times height. Just cut this thing in half, we have a triangle. And the other one, I add this because I can add a little bit of complication to it, is where it comes up, hits a peak, and then comes back down. And this is a trapezoid, and you should know this. This will help you on the ACT as well. The area of a trapezoid then is 1/2 base 1 plus base 2. It's a lot like a triangle times height. So it's just like a triangle, a little more complicated. Now we have two bases. We have the base here, and we have this new base because they cut off the top. So 1/2 base 1 plus base 2 times height. So all of these would be examples of impulse. Okay? All right. So in general, we're looking at, these are the only three we'll do. Now, I want to make a note. If you're doing calculus, you may run across this in your calculus class, where you have some kind of force times time, and it looks like let's say the graph looks like this. It comes up and then has some sort of a double hump, some kind of a camelback. Then you would have to determine that function, okay, whatever that function is, and then it would simply be, if this is 0 time and say that's 15 seconds, you would then take, now just ignore me if you're not in calculus, but then the impulse would be the integral, okay, because we're looking at, whenever you say area in here, we mean integral. In calculus, it would be the integral from, say, 0 time to 15 seconds, whatever that function was, f sub t, with respect to time, okay? So you can do antiderivatives, and you got it, you know, so there's one of your applications of your calculus. Okay, so let's get rid of all that and go back and work this problem. So here, looks like it says how much impulse is represented by the following graph. So all I got to do is go ahead and find the area. So 1/2 base 1 plus base 2 times my height. And base 1, I'll make this one base 1, that's 52. Before it's supposed to go right there. So it's 1/2, and I got to be careful with my units. 52, and these are milliseconds, so 52 milliseconds plus, and this one goes from 33, so 30, if that was 13, it'd be 20. So we're looking at 19 plus 19 milliseconds. There's my base 2 times my height. Now the height, that is F max. That's not F average, that's F max. And that's 30 newtons. Okay? So I punch all that in. And that's right, 33, 34, 20. Okay, so I'm looking at 52 plus 19 times 30. And then time divided by 2. And I get 1060. So 1065. But if I leave it like that, you're going to lose a lot of points. I mean, more than just normally you would. Because now the units are so important here. It's Newton dot milliseconds. Don't say newtons per millisecond. You can just say Newton milliseconds. But I like to throw the dot in there to indicate that you know that it's not being divided. It's Newton milliseconds or Newton dot milliseconds. Either one's right. So there's 1,000. So that represents an impulse of 1,065 Newton milliseconds. You can kind of think of this as, this is how much impulse I have to work with. Now how's that going to change the momentum? Because remember that impulse not only equals force times time, that also equals the change in momentum. So you can do a lot of stuff, a lot of information is tied up in this area underneath this curve. Okay, so we know we got 1065. Let's get rid of this other stuff. And now it says, what's the maximum force? Well, that's just 30 newtons right there. What's the average force? Now this is a little more tricky. There's some student that always raises their hand and says 15 newtons because it goes from 0 and 30. That would be true. The average would be 15 newtons if we had this box shape. If that was 30 newtons right there, then yes, I agree, the F bar would be 15, but it's not. It spends more time down here. So the F bar, for our case, is going to be something other than 15. Let's get rid of that. We have to go through, the only way to do this is to go through and solve the impulse equation. It's going to mess some students up probably in the next exam. Impulse equals, we said, it's really impulse equals, in our case, average force times change in time. All right? So if we already know the impulse is 1065, so we have 1065 Newton dot milliseconds, and then that is our impulse. If we divide that by our change in time, which is 52 milliseconds, we will have our impulse. And so we divide that out. We got 1065 divided by 52 and 20.5. So 20.5 newtons. So I should go back up on the graph and look at this and go, okay, that's 2/3 the way up. There's my average, put that in blue. There's my F bar right there, approximately. F bar. So the way you show it is, this is average, so it stays constant throughout the whole time. So I'll ask you on the next exam, I'm sure, to plot this. So I come up, and it's going to be a flat line all the way, you may use your ruler, all the way over to the end. So really, if I take the area, this area here represented by the trapezoid, and compare that to the area underneath this blue box, or this blue square, it's the same area, okay? It's just that the trapezoid is a lot better descriptor of what happened. You know, this is a blunt instrument. I put on 20.5, and at 2 seconds I gave it exactly 20.5 newtons, and I gave that exact newtons until 54 milliseconds, then I stop. Well, we know that's not true, but that's kind of, it becomes a gross approximation of what really happened. But sometimes in an equation form, you're kind of stuck with that, especially if you don't do your calculus. Okay. Then finally, the last question is pretty trivial. Which force do you use in the impulse equation? And I would use my average force is what I used. Okay. So there's number 6. I'm going to go right to number 7. I think I have time. They're going to come on with the announcement in a second, but we'll keep going. We'll just talk right through it. And so the next one's much harder. It's still the same idea of a graph, only now it's sort of backwards, as Britt said in third hour. Sorry, now I'm dating my years, but I'm doing this in 2009. And like I say, you might be watching in 2020, and we're all flying around in, space cars and stuff. And you go, man, Askey looks young. That old fart. Anyway, I'm 49, I'm young. All right, so graph the following: a maximum force of 800 newtons. Well, so let's get our, now I'll tell you what, on this one, I can already see it, just glancing at it, that we're going to have some issues with our units, because I saw a newton there. Here's a 88 millinewton dot seconds. Here is a, I think that says 30, and here's a 50, and oh boy. Now these are microseconds, so we got newtons, millinewtons, seconds, microseconds. That's why in the first few weeks we learned the metrics. I'm not just messing around. It wasn't busy work. We have to actually be able to now apply them, and you're expected just to know them. Now, it may be 2020, but I probably still have that thing hanging in the ceiling with all the different prefixes. Now it's probably a hologram. All right, so graph the following. Well, we know our maximum force is 800, so it looks like I can go ahead and set this up. That's going to be 200, 400, 600, 800. 800 newtons. And my area, the impulse, is 88 millinewtons dot second. So I see groups go to the board and work this problem, and I see them do it every kind of way you can think of. I'll try and show you what I think is the easiest. I can't see. I covered up that. Okay, that's 30. So I know that's equal to my F bar times And I can't use that 800 because that's not F bar, that's maximum. Well, let's plot what we can. The force reaches its maximum in 30 microseconds, so I guess we're just going to start at 0. And now I got to figure out how to plot this. Well, it's going to hold it to 50, so that means for 30, so we had 80. And let's assume it's going to be some kind of a not symmetrical. So if I go 10, 20, 30, 40, 50, 60, 70, 80, 90, 110, 20, 30. I'm trying to think what this ends up being. I have a key somewhere because I don't want to go off the graph. That's really hard. I mean, on the test or exam, I would say I would have it laid out for you. At least it'd be probably enough to give you so you wouldn't have to sit there and kind of keep guessing. But maybe let's go ahead and make the assumption that we're going to stay on the graph if I make that by tens. So maybe wrong. It's okay. So reach it in 30, and I'm going to go all the way to 800. So I know this much. I'm going to go up to 800 newtons in 30 microseconds, and it's going to hold that for 50.
This is your friendly reminder that it's time to start stars, so get a book, relax, stop talking, and read something.
Now, here's the problem. I don't know where to end up. I can't assume it's symmetrical, and so that's why this is where the students kind of hit a wall when they're working this problem. So let's think about it. We know that, okay, we also know that is the area of this thing, so maybe that's the way to go about this, is to determine the area. So let's go down and look at our numbers. 88 millinewtons dot seconds equals 1/2 base 1 plus base 2 times the height. Oh, okay, well I know some of this. So let's plug in, that's 1/2. That's my base 1, I don't know what that is, but my upper base I know is 50 microseconds, that is, times my height, which is 800 newtons. So, and that whole thing is 88, well this will teach you to keep units in your numbers, 88 millinewtons dot seconds. Well, probably a good idea is to go ahead and let's get, all I got to do now is solve this one equation, one unknown. I just got to make sure my units are all the same. So maybe we got to go ahead and do that. Let's convert this into, either convert this into millinewtons or convert this into newtons. I don't think it much matters. I'm going to go ahead and leave it. I'm going to put it all in millinewtons because I don't like to mess with decimals. So I'm going to do it in millinewtons, and I'm going to, because this is in terms of microseconds here, I'm going to go ahead and leave my, I'm going to put my force in millinewtons, and I'm going to put my time in microseconds. And so let's make this one, let's just go and leave this as 80. Okay, then, okay, if I'm going to put it in microseconds, that's a, who we got here? Jared? Okay.
Multiple.
All right, so I got, you guys come around, just don't hit that camera. All right, so I got, I'm going to put this in terms of microseconds. So, okay, so that's, so I'm going to be multiplying by 10 to the 6th microseconds per second, a little quick unit analysis. So that's going to put me at 88 times 10 to the 6th millinewtons dot microseconds, and then that equals 1/2 base 1 plus 50 microseconds times, and now I'm going to make this in terms of millinewtons, so that's 800,000, right, millinewtons. Whew. So now it's all over but the number crunching. I don't want to do that. That looks like a mess. So let me find my key. These nice young men that just came in, they can number crunch it for me, I suppose. Here we go.
Question?
Let's go right. Let's pull that cake out of the oven here. It's already done, of course. Little Martha Stewart here. Son of. Okay, so he didn't do the work. Well, it looks like it turns out that B1 ends up being 170, oh man, microseconds. It's going to take me off my graph, right? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, dang, going. So we'll go like this. It's going to go over here, and it's going to end up at 170. You guys shouldn't be watching this.
We're not in physics. I'm not in physics.
Oh, look, that was Jared.
Jared's
that's cool. Okay. You guys. Mr. Telescope Man. You guys come on up. Come on stage. Come on over. Come on in. Come on over. Little guest appearance here. Hi there.
Do you have desktop printers in your room?
Oh, are you from Lexmark?
Well, I'm actually with the district. They're with Lexmark.
Okay, yeah, I have a printer in my room. Go talk to the people.
I'll take it from you.
Okay, here. I have Lexmark printers on.
Yeah, we'll just
Hello, everybody.
see what we have.
Okay, so
We'll come on.
it's a Dell computer, and then come over here. So it's a E.
Okay, so basically, the impulse
it's
is
E3.
going to equal the area under the curve, which just happens to be 88.
Okay.
Just a second. Hello, just a second. Which you already discussed.
I did.
So yeah, not that hard, and we figured out that area equals 1/2 the B1 plus B2 times the height.
I have no problem bringing it back.
It's really not that bad. The only real thing is the frustratingly mixed up units that are in here, which just caution.
Okay, in that case,
Watch out
I'll
for
put
your
it in the mail.
Yeah, you gotta watch out for your units. 'Cause
Is there
Always watch out for your
this is
units.
usually, you always want them to be in the same tenths, like 10 to the 8th or 10 to the 7th, stuff like that. So,
Okay, I'll send it to you tonight.
this is really a tough one.
You bet. Bye bye.
So B1 ends up being 170. Yeah, that makes total sense.
Okay, we good? You guys approve? Are we clear?
I
All right.
approve.
All right. So good. So I'm going to wrap it up. Thank you all the guest speakers there
Yeah.
coming in from their long ride on a beautiful Friday afternoon.
Yes.
Now this is 2009, so they're not on their hovercrafts or anything. They're just on their bicycles. These old days. Not in a horse and buggy, but okay. So this area, then we're saying all this area right here, that was our 88 millinewton dot seconds. And I'd like to just give you worksheet after worksheet after worksheet of this stuff, but unfortunately it's a survey course, so we can only touch on stuff. But anyway, that's kind of cool because once you know that, then you know a lot about what happened in the collision, and it's an approximation. But very good. So that's 6 and 7, and you're ready to go.